I just want to revisit this, right? So you guys remember the voltage, right? Remember banks have volts and voltage, right? And the bank is the battery. Okay, it's where everything gets picked up, right? And it's filled with joules, and joules are energy, right? And then the vehicles, right? The vehicles would be like the current. They carry the energy around the circuit, right? Or around the delivery route, okay? And then it always returned back to the bank to pick up more, right? And then we learned that direct current, what we call DC, was like one flow, right? It just always went in one direction. It was a one-directional delivery route, okay? And then we had this thing called resistance, which we said was rough road, right? And it causes the trucks and vehicles to lose their joules of energy, right? And remember, in order for the vehicles to come back to the bank, they have to lose all of their energy, right? And that's what the resistance does, okay? That way nothing heats up too much and causes issues, right? If it loses all its energy inside of the circuit, right? That's what it does. So I kind of typed this after the fact, after I remembered all the, before I remembered all of this traffic model, right? But you guys can imagine, and this is kind of obsolete now because we're out of like the stage 3 lockdown, right? But circuits wired in series, okay? Series would be like you only have one choice in direction, okay? And that's what we're going to look at. This is what we call like series would be the simpler of the two, right? So these are the simpler circuits. I don't even know if that's how you spell simpler circuits. Okay, so these are the ones that look kind of easier, and you guys will know when you look at them, you'll go, okay, this one looks easier relative to what we'll see this afternoon. Okay, and so imagine you're entering a store, especially like under like COVID protocols, right? And if anybody had been to Costco, you would have seen this, right? When you enter the door, there's only one entrance and one exit, right? And so like I think this is actually normal under normal circumstances. You only have one entrance and one exit, right? But then people can only enter and exit the store in one spot, okay? And they can really only move in one direction around the store, kind of. I mean, there's some flexibility, right? But under COVID protocol, right, you were only allowed to buy essential items. And you'll notice if you went into Costco during that time period, all these non-essential aisles were kind of blocked off. And so, like, when you entered Costco, you could only really follow one route and out again. Okay, and this is what I'm just trying to get to, right? So like related to you guys in a sense of like something you've probably already experienced, right? So same thing here. Everybody enters Costco and they really only have like one choice in terms of where they can go, right? That's a series circuit, something wired in series, and there's only one option, right? You just go in direction. And so if we were to introduce some resistors like we see on this circuit, right? Well, turns out for a circuit wired in series, you can combine all three of these resistors to give you just one resistance value, okay? And basically you're just going to add them all up, right? Because you guys know, let's think back to our traffic analogy. You know, the trucks are going to leave the battery with some amount of energy, and by the time they come back to this, they have to have lost all of their energy, all their joules of energy, right? And so every time they go over one of these bumpy roads, they lose some energy, and then they lose some energy, and then they lose some energy, but you know they have to lose it all before they come back here, right? So we're able just to add them all up, all these different patches of rough road, and we figure out how much energy, what the total resistance is in a series circuit, okay? Do we have any questions on that so far? If you always think back to the analogy really helps, okay? Even not doing this for a long time, and like a long time for me is 2 or 3 years, I haven't looked at stuff like this. I think back to that traffic analogy, and it keeps things straight in my head, Okay. So we can see, you know, in a series circuit, the amount of, remember voltage is related to the potential energy that something has, right? So like how much energy or how much work something is able to do, right, based on how much energy it has, right? And so what you'll find is the voltage, I'll erase all these lines because it just convolutes things. The voltage at any particular point, well, the entire voltage, we'll call this V series over here, right? That's what we want to find out. Well, if you found V1 here and V2 here and V3 here, when you add them all up, right, you guys also know that the amount of energy in a circuit, in a circuit that's wired in series, has to add up to be the total voltage that's at the battery, right? You can't just have more or less energy. There's no option for it, right? It's fixed. It's stuck here, right? You can't just like, you know, okay, well, how much energy do the trucks, or sorry, here, let me rephrase that. How many joules are still left on the truck here relative to here? And then you do it again, that's V2. Okay, well, we know that this point here is the same as this one, right? But this represents something else this time. It's how many joules are on the truck as they head into the second rough patch, and how much do they leave with, right? So if I want to figure out, like, let's say I didn't tell you what the voltage of the battery was, but I told you what the voltage at resistor 1 was, resistor 2, and resistor 3, you could figure out what the total the total voltage in the circuit is, or how much potential energy there is stored in that battery by adding up all the voltages. Okay. Now, this one's the easiest one, and arguably, well, it's like a pivot point, right? And I think when we're looking to solve like puzzles, we're looking for pivot points. And you guys saw with projectile motion, this could be like your friend time, right? Where like time pivots between things. Well, so the nice thing about the current in a series, remember I is current, right? The nice thing about current in a series circuit is we'll get back to our Costco analogy, right? Or our traffic model. The cars only have one choice in where they can go. They can't just decide to go off in a different direction. Like, they're fixed on this like copper highway wire, right? And so everywhere around this circuit, the current is the same, because the cars represent right? So how many cars we have on this road is the amount of current, and it can't change because the cars have no choice to get off the road, right? And so that's why we see the total amount of current in the series circuit is equal to how many cars are at point 1, point 2, and point 3. Okay, does anybody have any questions of that so far? Again, I think we're in context now. We're starting to see like this starts to make more sense. Okay, if we talk about cars and in their traffic analogy and joules of energy and things like that, right? We have to lose them. Okay. Okay, we're going to look more at some of Kirchhoffs laws, right? We're looking at Kirchhoffs voltage law specifically, right? And we're going to combine it with Coulombs law, right, from the last lesson. Okay, and what we're going to see, these are kind of like examples of some of Kirchhoffs laws. We're going to see more of them, right? This is Kirchhoffs voltage law. We're going to see a current law. These are for like series circuits that are wired in series, right, where there's only one choice of flow. And what we'll do this afternoon, we'll look at the more complicated version, right? But we're going to still have Kirchhoffs laws helping us. Okay, so we're just going to take Kirchhoffs law and we're going to combine it with Ohm's law, right? Ohm's law says the voltage, we can calculate what the voltage is if I know how much current there is and multiply that by the resistance. Okay, that's what that says. So all we've done here is we take what the V is and we say, okay, well, I series, or the total amount of current in the circuit, and multiply that by the resistance in the circuit. That has to equal the current times the resistance at each of the 3 points that are in our particular circuit, like for instance up here, right? So when I add I times R, I get the voltage all the way around, right? And we know that in a series circuit, remember this is just Kirchhoffs law for voltage. We get V series equals V1 plus V2 plus V3. That's all that's happened here. Remember we said voltage in series was equal to these things. Right? Okay, well all we did was substitute the fact that V equals I times R. And we just put little subscripts for each of them on there. Okay, and you see, for a series circuit, what ends up happening is, well, we kind of have this constant, right? We talked about the fact that like the current in a series circuit never changes, right? So it's like mass for your like mgh and 1/2 mv squared, right? You've got masses on both sides, you can cancel them, right? And we see, okay, well, we can cancel all of these. That's what's happened. And what are we left with? Well, it gives us a statement about the total amount of resistance in the circuit. And that gets back to what I said in the very beginning here, right? Like the resistance, when I add up the total amount of resistance in a series, I have to get the total amount, right? So that means if I have like, well, we're going to see an example here, right? But we know that the total amount of resistance in a circuit is equal to what happens when I add up each of the resistors' values. That was this, right? I said this at the very, very beginning. And now I've just shown you where it came from and why it's true, right? I can add this to this to this. I know that when I do that, the resistance in a series, I can just combine into one really big resistor. That makes sense? Everybody so far? Okay, so the first example is really easy. Okay, series circuits are the easy ones, right? Because the current or the cars don't have a choice in where they go. They're stuck on this one track and that's it, right? So when I come down here, this first example just wants me to calculate the equivalent resistance in a series circuit. Okay, so what do we do? Well, we've got what looks to be 4 resistors, right? We know, based on above, I've got to add up R1 plus R2 plus R3 plus R4. Okay. What do you get? Well, we get 41. And remember, the ohm denotes resistance. That's what you guys are looking for, right? If you're ever like, oh, what 41 what? Well, ohms is resistance. You know, the V is for volts, which is potential. And the amp, or capital A, stands for current. So if you guys are ever given any numbers, you just look at what you're given and then associate that with what it actually means. Okay, so we're going to have 41 plus 51.75 plus 11.1 plus 1002.008 ohms. Okay, those are all in ohms. And then we add it all up. I actually haven't done this question yet. Easy enough though, but I'm not going to do it in my head. 0.75 plus 11.1 plus 1002.008. Okay, and you get a total resistance for the circuit of 1105.8 or you could call 0.9 ohms. Okay, so you could condense if you had a battery and you had these 4 resistors normally, you could just draw yourself one really big resistor instead of 4 little ones. That's all that means. Okay? So if the cars only have one choice of travel, right, then they have to lose all of their energy, right? Doesn't matter where along here it occurs. It just matters that they lose it all before they arrive back. Okay, that's all this is saying. We can write our series. Okay? So what I want to show you guys, okay, that's relatively simple, nothing too crazy there. We have this, okay, and I'm just going to pull this up because I have this filled out. Okay, this is like a good little sheet for you. Okay, so you guys keep this, and then you'll use this later. Okay, and this is a good little summary sheet. It keeps everything straight on one piece of paper whenever you're looking for something in particular, right? So we have a bank, right, and we have rough road. Okay, and along it we have cars that are traveling. I'm gonna try and draw a nice car, right? And they're going around the track or road, right? And across the rough road, they're depositing their joules of energy, right? They're falling off. Okay. We know going from here to here that there's joules, right? Which we know as being energy, right? We saw the unit of J across our entire unit of energy, right? And then around our circuit, we have electrons flowing, right? Which we call the cars or trucks, vehicles. Okay, so what I want to do is just come down here and fill out this table quickly, and then I'll do one question, and then you guys will be pretty much done. There's a couple homework questions down at the bottom. Okay, so this sheet's like pretty important. Keeps track of everything, right? So we know, and maybe we don't know actually. We haven't necessarily exactly talked about this, but the charge. If we were looking for a charge on something, like on, let's say, in grade 12, you guys will see something called Coulombs Law. That's what the 4Us are actually doing today. And we denote charge with a symbol of Q. Okay. Energy we call E. Current we've seen as being I. Electric potential or voltage we've seen as capital V, maybe with the two sticks on it. And maybe I'll do one other thing too. I'll write in here, how do we actually calculate it with the formula, right? So we'll say I. We saw the amount of current was some amount of charge, right? Remember, it was a coulomb. Well, we did see what a coulomb was. It was a, if you guys remember the cube, right? Full of all the electrons, right? That was 1 coulomb. And we found that the current, or how many electrons are flowing per unit time, was the charge on them, right? The charge on the coulomb divided by how many we saw per unit time. Okay, so this would be how you would solve for current. Electric potential, we saw voltage was equal to, remember we used the funny V so we could denote it, was the amount of energy, right, E, divided by the charge. That created the potential. And you guys also saw power, which we said was P, which was the voltage multiplied by the current. Okay, below here, I'll show you where this comes from. I'll try to do it neatly and small. Might change the pencil size here. We saw power. This is just a derivation of it. E over Q. So the energy per charge multiplied by Q over T, time, not capital T, that looks like temperature, and then multiply that by E over T. And what falls out? Well, we see Q's drop out, and oh, did I write that wrong? No, E's drop out. E's should drop out. Oh, sorry. It's not. There's not a multiplication sign there. One sec. Sorry, guys. It's so small. My solutions too. Oh God. It's an equal sign here. Okay. So that's another way you can calculate power. It's the amount of energy per unit time. I think we saw that one too in your readings about power. I want to erase here. Okay, so you get two definitions for power. Okay, and the last one, resistance, came from Ohm's law, right? Which it stated R was equal to the voltage divided by the amount of current. Okay, so this is what I'm saying. It's so easy, and this is why I created this table, and why the traffic analogy exists too, right? Like, these variables are weird, and even in writing that right now, like, I feel worse about some of this stuff now after writing that than I did 5 minutes ago talking about it. You know what I mean? Like, these things are awkward and weird equations. Okay, and individually, we could talk about these things individually, no problem, right? It's when you start putting them all together and asking questions, like, it becomes convoluted because they're weird. They don't have normal meters per second. You know what I mean? It's just kind of a different can of worms, if you will. Okay, and so the traffic, and this is where the traffic analogy comes into play. Like, we can think about the potential as being the number of joules at the bank, right? And the current being cars and sorry, I thought I saw somebody type in the chat, and resistance being rough road and things like that. Okay, so the units down here, we're going to have the Coulomb, right? And I always misspell Coulomb, C-O-U-L-O-M-B, right? Which is the C, capital C. We have joules of energy for energy, right? Which we denoted as capital J. And we have amperes, which we denote as capital A. The volt, right? Which we saw as being an amount of energy, right? I'm just going to put it's like a dimensional analysis, right? We have joule per coulomb. Like, we've seen this before, and we denote that as being a capital V. And then we have watts as for power, right? Which is W. And ohms, which was omega. Is everybody okay? In the traffic model, right? Charge was charge. Let's jump over that for a sec. I don't know if that's right or not. We have joules, right? We have, oh, right. We have the cars themselves. Sorry, let's be specific. Charge is the car itself or truck. Current is the number of cars. Okay? Per second driving by. Okay? Electric potential is the number of each car picks up. Okay, or drops off. Oh, that's true too, actually. Or drops off. We saw that we could have an electric potential that was negative, right? That's when they dispose of their energy, right? If you were to measure a negative electric potential or negative voltage, you would know that they dropped off their electricity, or not their electricity, their energy, right? And power was the number of joules per second getting dropped off, right? Okay. and resistance was the bumps in the road. Does anybody have any problems? Freaking out. This is like a recap of everything that we've kind of seen. You guys did a little bit of some of it in the energy unit as well, right? Power and efficiency, and then for the last couple of days, we've been spending time on like what's electric potential, what's resistance, and what is current. Okay, this is very scary stuff. I think I don't know if you guys are freaking out right now. I remember the first time I've seen this, all that stuff was like, they're just weird units, right? Like normally we're dealing with nice things like meters and seconds and kilograms. Like, what is this stuff? It's just different, you know? So it's scary from that perspective. But if you think to this traffic model, okay, it's going to make things like this so much easier. Okay, this is like, we want to find the total resistance in the following circuit. But the problem is, you know, unlike the question above, I didn't tell you what the resistance was in each of these spots. All right, so it's not as simple as just going, oh, resistance 1 plus resistance 2. We've this is what I mean, it's kind of like a puzzle. We've buried particular information in spots around the circuit, and you guys have to use your knowledge of this traffic analogy to figure it out. Okay, so we could, I don't know, this, anytime you guys have two pieces of information, right, like here, you could find the third, right? So let's do that. Well, how would we calculate the resistance? So, well, the resistance is the voltage divided by the amount of current, right? So let's say, okay, well, we got resistance R1 would equal V1 divided by I1. Okay, well, V1 was 4 and I1 was 3. Okay, well, that should be, oh, what is it, 1.25, am I right? 4 divided by 3? 1.33. And what are the units? Ohms, right? So you get to write that on that line now, 1.33 ohms. Now, there's something else here. We know the voltage at the battery is 6 volts. And what did we say about the voltage? What did Kirchhoffs voltage law say? Well, let's go up and have a look. Kirchhoffs voltage law says that for a circuit that's wired in series, I have to add up all the voltages, right? In other words, you know, the voltages have to add to 6. So I know that VT, so if I found, what I'm looking for here is V2. We know that V2 has to equal the total voltage, VT, minus V1. Right? Because V1 plus V2 has to equal VT according to Kirchhoff. Right? So if I were to solve for V2, voltage 2, not velocity, I'd find what the voltage is at resistor 2. Okay, so let's do that. Well, we know that voltage total was 6, and if I subtract off voltage 1, that was 4. Okay, well, I know that the voltage here must be 2 volts. Now, using one of Kirchhoff's other laws, we could also figure out what the current is at resistor 2, right? Or if you think back to your traffic model, this point here at point 1, it's telling us that there's only 3 cars on this road, right? But they can't just decide to, like, it could even be a train track, right? It can't just decide, one of the cars just can't decide to go, oh no, I'm not following it anymore, right? We know that the number of cars for a series circuit has to be the same. right? So if you see that the current over here at I1 is 3 cars, then you better see 3 cars of current down here. And you better see three cars there as well. Okay, and the only other thing to do is to find what R2 is. Well, you could just do the same thing that we just did here. We've now found the other information that I need, right? We know that R2 is going to be equal to V2 divided by I2. Right, same thing. So V2 was 2 and I2 was 3. That'll be 0.66, right? Even 6.7, we'll call it. So what is the total resistance in this circuit? Well, for a series circuit, remember, when cars leave with their energy, they have to lose all their joules before they're allowed to return back to the bank, right? So how much resistance is there that causes the joules to be lost? Well, you add them up. So we know that RT will equal R1 plus R2, which will equal the 1.33 ohms plus 0.67 ohms. Okay, and we'll see 2 ohms of resistance in the circuit. Is everybody okay with that? Remember, the series ones are like, if you see a series circuit, that's your friend. They're a little bit easier to navigate, but not too bad. Like, even if I show you a more complicated one, it's honestly not that bad. It's sometimes a little puzzle. You got to sit and stare at them a little bit sometimes. But that's what we're going to spend our time doing this afternoon, okay? So there's a couple of questions there. Remember, if you guys are really stuck, you can build these things, right? You can input the information and play around with it and see what happens. Right? You can build them in the FET software. Okay?